Hi, everyone. Thank you so much for joining us today. We'll get started in just a few moments here. Thank you. Hi, everyone. Thanks for joining us for ACPI-Lite, exploring a simplified mechanism for abstracting platforms with ACPI as part of the UEFI 2021 Virtual Plugfest. We wanted to take a moment here to introduce our presenter. So we have Andre Warkentin, who is an ARM enablement architect at VMware. And with that, I'll go ahead and pass this off to Andre.
Thanks. So today we'll talk about ACPI and the context around how it's evolved over the years and why some further evolution may be interesting. And whereas in this presentation, I will talk about some potential for improving ACPI. It's not meant as in sort of an exhaustive analysis of all areas where ACPI could be changed or adapted. And it's not a I'm not proscribing anything. This is more food for thought and for a healthy discussion. So what is ACPI? It's a set of firmware tables that are used to describe the hardware to an operating system. And it's a set of interfaces between the OS and the hardware to describe configurations such as how to locate certain devices, what memory ranges, what interrupts they use, and also for power management. So how to enter low power states, how to enable devices, disable devices. Now, traditionally, ACPI has relied on ACPI-specific hardware, although that has changed as ACPI evolved to support non-x86-based systems. But one thing to take away is it's not really just a physical description. In many ways, it is an abstraction modeling originally what was a typical or ideal x86 system. In many ways, this ideal system did differ from the actual underlying hardware, and this was possible because ACPI used bytecode to perform this abstraction. And of course, the idea that this description as abstraction is provided is agnostic to the operating system running on the hardware. Like I mentioned, there is a dynamic component to ACPI. And for those of you familiar with device tree, sort of a similar concept, but it's a program. Unlike device tree, the AML bytecode is a program, and it generates the ACPI namespace within the operating system that runs that program through the AML interpreter and forms this hierarchical description of platform devices. Methods are used to abstract actual device or platform configuration. For example, you may have a method that returns the current configuration, CRS, of the resources. And interaction with actual hardware is done using something called operation regions, which are implemented by the AML interpreter and represent the interface between AML and the underlying OS it runs on. This way, AML bytecode can poke at memory, poke at I/O registers, and do some other interesting things. Recently, many of the extra new operation regions added involve platform-specific OS drivers. There is a static component to ACPI as well. These are used for early initialization at things like timers or locating CPUs for secondary initialization. Of course, I mentioned device tree. What is device tree? Those of you familiar with the ARM space, over the last few years, been quite a bit of it's called a battle, of contrasts, whether ACPI is appropriate for systems, device tree is appropriate for systems. What is it? It is a hierarchical tree data structure which encodes device characteristics. In this way, it sounds a lot like ACPI. However, there are no methods. There is no abstraction. There's no interpretation. It really does just describe all the information a device driver or operating system needs to drive the platform, to drive the devices. The roots for device tree are from the open firmware. Device tree was the result of an operation called flattening. As the early bootloader or kernel portions would traverse the open firmware device tree, and it would be traversed using client interface calls and collected all this information to make it available to the operating system when open firmware will be shut down. Device tree came about and was adopted in the early tens of this century as a way to solve issues supporting different kinds of PowerPC and ARM platforms, and of course different adaptations of these platforms. Great thing about device tree, of course, is the minimal support logic to support it. It did come from Linux and is actually very closely bound to Linux. In many ways, operating systems such as BSD today have trouble maintaining device tree support because it can and does change in a random manner of operating systems. The idea of device tree, though, is that the entire adaptation of the platform for an OS is entirely owned by the operating system. There's no abstraction. If you have a funky device and there's a set of integration quirks, everything must be described, and then, of course, the driver needs to be able to use that information. In many ways, the device tree is a contract between it's a contract. And the information for a specific device and the device tree is a contract between the firmware developer and the driver developer. The hardware developer and the driver developer, which many times, if you look at, let's say, ARM systems, that's the same company. So what are some challenges of the ACPI? Again, I'm looking at this from my prism, which has been working on ARM systems for almost a decade. ACPI, in many ways, has been described as an overlay on top of what a typical x86 system looked like at the time. And although the folks behind ACPI had the foresight to understand that systems will change and have provided the ability to abstract it using this virtual machine called AML, the AML interpreter, describing or abstracting non-x86 systems is actually still a challenge. So that's one aspect, and we can kind of take a look at that. Another one is ACPI usable for every single use case? So it's usable for server systems, we know that. It's usable for customer systems like laptops, we know that too. But is it suitable for embedded systems? Is it suitable for safety critical systems? So that's a problem as well. And so what my opinion is ACPI can evolve to meet ACPI. You can look at it as a set of tools, really, and it means we really can evolve this mechanism to meet separate goals. So my take is that ACPI can become better at describing hardware, right? Now, again, by describing hardware, I don't really, and I know folks are going to have a comment here saying, well, why would you want to describe it? We should always abstract hardware, right? What I'm trying to say is, well, what if there's hardware that you could describe, right? Very relatively standard hardware. In this case, does ACPI give you all the tools today to describe this hardware without relying on platform-specific OS driver components, okay? Another one is be able to be better at abstracting hardware, which is to avoid platform-specific drivers entirely. I don't mean, of course, you can't avoid writing drivers. That's not what I'm saying. I'm not saying we won't be writing NIC drivers or storage driver. What I am saying is that we should be avoiding the need to write drivers for critical parts of system functionality. Right? You should need a special driver, for example, to notify that there's a hot log event happening. Of course, all in all, I look at ACPI as a mechanism, and so these goals of evolution, there are more about capabilities, not policy. So, actual policy of which of these parts of ACPI as they change could be used really does depend on the use case. So we'll take a look at that. Again, why do we care about evolving ACPI? A good question somebody might ask is, who cares? Let's not use ACPI for real time. Let's not use it for embedded. But device tree doesn't really seem like a great choice. As I mentioned, it is somewhat bound to Linux. Linux is a primary user of device tree, and many of the properties or information presented by device tree nodes, they're really meant for Linux drivers. This heavy intertwining does present a problem for other operating systems. Another one is device tree doesn't really abstract anything. So no matter how small or insignificant the change, if your OS isn't ready to cope with that, then that's it. To be honest, many of these platform differences could probably be encapsulated fairly easily. I mean, they have been traditionally with ACPI, and in my opinion, there's little benefit proliferating differences. Now, why not use ACPI for real time? I don't know. I think that ACPI does present a good value proposition. You could call it a hardware and firmware contract, and it does simplify the way of how you port an operating system to new systems. It's great to avoid extra platform-dependent code in the operating system. So imagine if you had two different cards that were different in only minute ways that didn't really impact any of the workloads. But today, if those platforms use device tree, then you would actually, you may have to adapt your platform code to support that. Again, not every OS is Linux or Windows. Generalizing OS specific extensions assumptions is a good idea. And one thing that resonates with ACPI for me is that as you push quirk handling and abstract the kind of the low-level details away from the OS, that means you push the ownership of those quirks and the maintenance into the firmware and not into the OS. This may be a contentious subject as well. Some folks may feel that it's better to keep that stuff in the OS, but to my opinion, it's not good to keep quirks and low-level platform behavior workarounds in the OS because there's no good timeline for cleaning that stuff up, right? So the OS vendor, OS developers are stuck with this stuff forever and ever. Okay, well, of course, folks will say ACPI already does do a pretty good job of abstracting non-IA platforms. Of course, ARM servers use ACPI. And this all goes back to ACPI 5.0, which introduced something called reduced hardware mode. Now, this removed the requirement for this fixed function hardware, ACPI function hardware, which is great because you could hypothetically take something like an off-the-shelf ARM SoC and start using ACPI to describe it, right? Kind of, except now for those parts of the spec which relied on fixed ACPI hardware, now you need to use OS-specific drivers. A good example of that is instead of having a common mechanism for signaling events, now you need to rely on, say, a GPIO driver to be present in an operating system if you're signaling events using GPIOs. Many of those parts you threw away the fixed ACPI hardware because the systems are just that different. But now, in order to fill in the gaps, you need extra code running in the operating system. For example, there is a vendor-specific, a Microsoft-specific extension called platform extension plugins, which actually amounts to having code running in the operating system that is executed in place of AML mechanisms, which means where if you need to do something that is actually not possible to do within the ACPI, well, this is your kind of get out of jail ticket, and you can run code inside an OS. And why would you want to do that? Well, AML is a bit primitive, and does provide fairly high overhead. For example, if you wanted to have some kind of asynchronous communication with hardware, let's say you're trying to write a time and alarm device, and you don't want to rely on an I2C operation region because again, that will usually involve an OS driver. If you want to do this using low-level primitives, that'll be pretty hard. You have code that literally would just like sleep for 5 milliseconds, come back, and wouldn't really work very well. Another area where AML is a bit primitive is if you're communicating with hardware, just say cache coherent, or if you really want to make sure that a special kind of access does actually amount to be, let's say, a PCI atomic. If you want to have some kind of a barrier, explicit barrier between different kinds of memory rights, you couldn't do this in AML today. And there is also, I should note, no standard way of quickly escaping out of AML into even some higher privileged code to take care of some of these complications, right? Really outside of x86. In x86, you have SMM, is yes, heavily frowned upon, but it is used today, specifically, where code and AML, if things get a little too difficult, it can just touch a special register, a special memory location, and there it goes, an SMM doing something more complex. Again, we're talking about mechanisms, not policy. I can imagine in some use cases, maybe in server environments, cloud environments, you don't want to have this sort of cycle stealing or SMM, a trust zone, but to really not have any mechanisms to even be able to do that does actually prevent you from using AML in places like that. Okay, now, as a result of ACPI getting adopted by ARM systems, we've also seen that the line between ACPI and device tree is getting erased somewhat. There's a way today by which ACPI devices can embed device tree properties, which actually allows you in a Linux operating system to have a driver that can bind to both device tree devices and similar worded coded devices in ACPI. For example, the way it works is that you use a special hardware ID, PRP0001, and then a special mechanisms for just encoding key value pairs, which directly map to the device tree properties. So that's kind of weird too, because now ACPI is just used more and more to describe all the same sort of platform-specific stuff, right? Again, it relies on the driver knowing you should look for a special property to get some special values out. Again, so that's kind of weird too. You're now describing and abstracting. And even if you thought that was a great idea, well, today ACPI somewhat even trails, both in being able to one-to-one describe the exact same platform with device tree, to be able to describe that with ACPI. Issues like how do you describe hierarchies of clocks, how do you describe power source dependencies, composite devices. But then again, maybe we shouldn't be maybe the problem is even bigger. The problem is if you wanted to abstract those things, not just describe, then there's even more trailing behind. Okay, so let's say you wanted to run a small real-time OS. You build it from scratch, and you really wanted to run on ACPI systems. Well, let's say it's part of a safety critical system, and your code really need to get audited, and there's specific rules you need to follow around software engineering. Would you just take an AML interpreter off the shelf and embed it? Probably not. ACPI-CA is 331,000 lines of code. Yes, there's a lot of comments in there, but nevertheless, you can imagine writing a fully compliant AML interpreter. Right, fully compliant to what? The spec is over 1,200 pages. Is a significant effort. ACPI interpreter involves significant OS support, mapping memory, locking primitives, timers. So in fact, you can't use AML in fairly early boot code. AML is interpreted. It also has a single global lock. So you can say it amounts to being slow. And the high complexity mean that it's hard to prove that it's correct. It's hard to write it from scratch. So what can we do about that? Okay, now here's where I can put on my what if hat. Now, what if there was a valid subset of AML that did not require a proper interpreter, right? So you had strict rules over how, for example, methods returning resource data were formed, which means I would call these canned encodings. So effectively, you could have a small AML support system that would only work with devices described in a very special manner, right? So in a very kind of well ordered, it has strict scoping rules. You didn't really have any control flow. Um, you just had a simple way of describing static data. Will this be useful for anything? Well, first of all, many of the simpler system on chips don't really need dynamic behavior. Kind of just saying, here's my USB controller here, and here's my PCI, root complex over there. And if you just make this a restriction on what can go into a method, right, in what order, then you can still make it fully compatible with a regular AML interpreter. So maybe the pipe dream there is that I'm able to create a subset or describe or form my AML code in a way where it still is fully regular AML that can go through ACPI-CA, but yet I'm able to write a lighter weight implementation inside an ACPI OS that will support this simpler variant that doesn't allow for arbitrary bytecode interpretation. That's kind of one crazy thought. Now, here's what I also like to stay back and talk about the value proposition of ACPI, because ACPI really means the benefit of ACPI is twofold. As an OS vendor, the benefit of ACPI, of course, is being able to abstract devices, being able to have a single common way of querying, what driver should load for which device, how to get its configuration, all of that. But for folks building systems, to them, ACPI really is talking about the initial source code that goes into describing the system, the tooling that they're used to. So if we take systems that are today traditionally built with device trees, so these are embedded systems where they usually U-boot as the UEFI implementation, and they use device tree. For those kinds of systems, what if you wanted to bring them into an ACPI world, right? One of the problems you will see is that those companies will come back and say, we have nobody who understands ACPI. We don't have the talent to go and develop it. So what if you started with just the device tree that these vendors provide, and you were able to compile it into this strict subset of ACPI? Clearly, it seems like you could do that because device tree is all static, and you're compiling into this again. It's a subset of ACPI. Clearly, the methods will only return static data or properties. And this could allow you to bridge this embedded device tree world with an operating system that only supports ACPI. Okay. So that's kind of one thought. Okay. Now, but what about abstracting? So this is the other point. I mentioned that one of the problems today with ACPI is that when we said hardware reduce mode enabled us to support ARM systems, that was great, but you could only do it by relying on OS platform-specific drivers. You need a GPIO driver, for example. You need an I2C driver. Let's say there may be even quirks there, but wouldn't it be great if? And I mentioned that some vendors already have a mechanism. It's non-standard. It's proprietary to that vendor, where they're able to use their own drivers in place of AML methods. So ACPI, an AML method calls another AML method, but it's actually calling into native driver. So that exists, but it's not a standardized capability. What if we could allow native methods where instead of running through an interpreter, it really just calls native code as sandbox. And this is made in a general fashion. It doesn't rely on any specific OS driver framework or anything like that. One technology that's being developed today, for example, is the platform runtime mechanism, PRMT. So the idea is that you could provide optimal implementations for those parts which are performance sensitive. If you had AML that was doing calculations, well, great. Maybe you could use you could contain so long as you could run the code, with in the sandbox. At least you'd run faster than AML. Okay. Another case would be that it also allows you to do things that AML is not capable of doing today. What if talking to a hardware involves being able to generate some very specific CPU instructions to guarantee that accesses are, not split across several instructions, that they can translate into, proper atomic kind of instructions, that you can add the right CPU barrier, that sort of thing. Or even, right, you could say that, fine, this native code may even use some firmware interfaces to go and do more complex stuff. So the idea that this native code is not, of course, distributed in the OS. This native code it's machine code, but it's owned by the silicon provider, by the OEM. It's somehow distributed with the system. So you could say that I'm looking for a standardized replacement for these platform extension plugins that we've seen on Windows on ARM, Windows on Snapdragon systems. They don't rely on OS-specific extensions. And again, the code really would be owned by the OEM and the SIP, and not the OS vendor. Now, what sort of things could you accomplish? Let's say maybe in some cases you wouldn't want to allow this, right? Maybe in servers you say, well, we don't want to defer to firmware code or something like that. But this is really a mechanism where you could selectively choose to use this mechanism. For example, let's say I wanted to implement a timer device using this native code. But I will keep but I don't have to switch all my AML methods to native code, right? So this would be an opt-in. And of course, I could imagine that you'd have to go on a case-by-case basis to see where a conversion would be actually necessary. Okay, so let's say for a moment you had the ability to have a reduced set of ACPI where there was no AML interpreter. You just support a certain canned ways of grabbing fixed data from ACPI devices. And whereas you needed the dynamic capability, you would have these native AML calls. There's no AML, native ACPI calls, which could be done using PRMT. They could be SMM. They could be trust zone. They could be implemented in any way possible. But it's native code, and it's code that's not part of the OS. Of course, you could pick and choose things as necessary, and still it would allow you to if you were doing this for some purpose-built development, you could have, you would end up with a lighter weight and more flexible ACPI subsystem. At the same time, because both of these facilities, both the native calls and the lightweight methods that will be part of the regular ACPI, then of course you would still retain capability with a more traditional implementation. So if you want to develop a real-time OS, support a small embedded environment, you could craft a system that could support such a system, whereas it would also support a bigger system, more general purpose operating system. Okay, so really what you could go and do with this, I would say, is see what this kind of reduced static AML could look like. We could do this today with the AML interpreter that we have, which is the ACPI-CA. Again, you could look at it from different perspectives. You could come up with new novel bytecodes that are just used to, new novel ways of describing a method that you'd clearly understand to be a reduced static method, something like that. Or maybe you could just sit down, go through the AML spec, and just write out, like, this is the specific way we expect a lightweight device to be described. These are the only opcodes that are allowed. These opcodes are not allowed. Some of the concerns that you may have is, even static description of devices sometimes rely on reading something from non-volatile memory, from like memory that's not touched by the OS, memory, ACPI only memory. Many times you could see that the same ACPI is used in different platform adaptations, and instead of updating the ACPI in place, the ACPI is written in a way where instead of just returning you the static value, it reads something from a memory cell and then adds a value to it, right? So of course you will lose the static methods. You will lose such a facility. But then on the other hand, so that's one thing. You could go experiment with that. And two, of course, try to build a converter that goes from device tree to this reduced AML. Now, the second part of the native AML methods is probably more complex. Again, you could do it with ACPI-CA. I would personally consider the different backends. PRM may be one of them. PRM is a technology that it's sort of like UEFI runtime, but it's pretty flexible. It's designed in a way where an operating system could even update and load newer PRM drivers. But maybe it could be pretty simple. Maybe you could just say that these are SMM calls or trust zone calls, raw SMC calls on ARM. I know some folks will have that. Or it could be just a more simpler UEFI runtime calls. Yeah. So that's kind of the story. Okay, all right, let's see. First question. Doesn't this enable encapsulation of platform specifics within the firmware with the assumption that this is always bad? Okay, so this is where my opinion, I'll share my opinion, is that as an OS vendor, VMware works on a proprietary OS. It's called vSphere. As an OS vendor for proprietary OS, there's very little benefit for us to encapsulate platform specifics within our OS. And I know that for other operating systems may see it a different way, but what I haven't seen for these other operating systems, I've never heard about the clear policy where platforms, what is the story for how long the platform quirks and assumptions live? Is it just code that goes into an operating system tree and lives there forever and gets maintained forever? Or here's another problem. Let's say I roll a quirk in. And the quirk, it's not just code that codes around some hardware bug, let's say, but it's always coded with the understanding that it fits in the current software architecture. If you have a whole bunch of code, that came from a silicon provider, came from a third-party vendor that I may not necessarily understand, but it was developed again in a specific environment. Right? It actually means that it's hard for me as an OS vendor to evolve the code around that quirk, right? Because now I need to somehow think, well, is it going to break this code? Like, what are the assumptions that this code made? Like, were those assumptions clearly documented? So what ends up happening is that I end up being the maintainer. As an OS vendor, I end up maintaining all these platform specifics, which I don't think I want to do. It's much easier to push the problem onto a firmware vendor, and then it becomes a qualification issue. It's like, well, our OS version 7 ran fine on your platform, but version 8 doesn't, right? I think you have a firmware bug. Please go fix it. Okay, wouldn't there be a compatibility problem to start redefining ACPI? I don't want to start redefining ACPI. What I want to do, again, when you look at the fixed static data, it's more about a subset, right? And again, I think the only way to do that right is to make sure that it's really a subset that works with the existing email interpreters. Now, native methods, of course, are just another feature. So there are many new features added to ACPI, every year. This could be one of them, and I would expect that all the big boy implementations of ACPI would carry that, much like how today different OS vendors are looking at PRM. Sorry. So yeah, I don't think it'll be a compatibility problem. It's more like you're able to create a lighter weight. You will be able to craft a CPI that will only be, let's say, supportable by Linux, Windows, and ESX, but not by like Zephyr. Okay, but you can already do that today. You can already write a CPI that will only be supported by Windows and not Linux. So that's a problem we still have. If the aim is to simplify AML and the subset is almost static data, then what are the advantages with respect to device tree? Okay, that's a good question. So in my ideal world, you still have the dynamic component. The dynamic component to me is very important. It may not be important to somebody, but it is important to me. So in my ideal world, I'm able to get rid of the complexity of the AML interpreter, which means for some methods are just static data, great, but others will be these native methods that will basically escape out to say secure world, or maybe there's sandbox code with PRM, something like that. Others may not see a value in the dynamic portion, right, and we'll stick to static data. At that point, the advantage of R is that it's still all in the same ecosystem of of ACPI, both from the tooling perspective as a silicon or OEM company, and from the operating system, where I don't have to support, two different device driver stacks. Like, okay, well, I have a way to support ACPI devices. I have a way to support device tree devices. Ideally, because ACPI really is, it's a separate spec, it's owned by the UEFI consortium, and the way that ACPI evolves does, it's much less volatile from my perspective than device tree. So I don't think there's like any one specific value proposition. If you're using device tree today, then yeah, like, okay, what do I get out of switching to ACPI? Well, for ACPI OSs, systems that are using ACPI today, this gives them the ability to let's say the native methods. So it will give them the ability to target hardware that isn't quite well describable using ACPI without relying on platform OS devices. And the static data, again, what if you wanted to have hardware that you support with a lightweight OS or a general purpose OS? Could you share some light on thread-safe ACPI methods? Okay, thread-safe ACPI methods. Today, ACPI methods exist. So they're non-reentrant, for one, and then there's a global lock. So one thing you can do, for example, is you can have AML code that, let's say, through an operation region wants to go do something, but the implementation in the operation region ends up calling other AML code. Beyond that, I don't think I can add any more to thread-safe ACPI methods. How is useful to have an old OS to run on new hardware? An old OS, okay. Is it still a strong case, as most maybe systems usually have all new hardware before, or maybe OSs, as most OSs usually have all new hardware before it all goes out? So I don't think ACPI is really a HAL. Per se, I don't think ACPI is really meant to be used as a HAL. I don't think it's really that possible to run an old OS. I mean, you're going to have a situation. First of all, there's drivers. That's the most basic part. But ACPI, well, you know what? That's a good point. ACPI by itself is a HAL, or at least ACPI that abstracts the hardware as a sort of an ideal platform. Yes, that is basically a HAL. So I do actually see a pretty strong case for maintaining ACPI to be a HAL. Okay, I don't see how this would work in real world or be less effort than supporting device tree directly in the OS. Okay, well, if I have an ACPI operating system today and I wanted to run on a system that is a bit tedious to support using ACPI, because many of there's a bunch of functionality that would have to be done in a platform-specific manner anyway. That's still less work for me than adding device tree support into the OS and then supporting effectively the Linux bindings for that system. Because when you say device tree, you're really saying, okay, where did the device tree come from? The device tree came from somebody who enabled Linux to run on that chip or system. So again, when I talk about native methods, in my mind, actually solve a problem. Well, they could solve a problem with device tree as well. Why is increasing the ACPI OS side support code for ACPI to include, why is it a bad idea? Because it ends up, well, it's first of all because it's more work. It's more code that has to be written. It's more code that has to be audited. It's and once you start down that path, it's work that now it's yours. You own it forever. Like I said, you have to start designing your changes to your generic code around this random platform stuff that you just added. And many times, unfortunately, I don't want to say it's gratuitous, but if you're just able to step back and come up on a standard mechanism for solving some of these issues, even things like abstracting, I mean, it's somewhat a different topic, but even like abstracting, today on ARM systems, you have a problem where many implementations aren't standard and you need like a custom quirk or custom driver to access the config space for PCI devices. And none of this is, of course, in the kind of in the fast path, but it's a whole bunch of really weird code that only hardware vendor understands, but it lands in your OS and now it's yours forever. You have to own it, and if you make some benign change and it blows up on the system, now it's yours to solve. That's why I effectively OS side support code for ACPI. OS side support code for platforms is code that is very easy to take in and it's very hard to take out. So having some kind of a firewall and keeping those specifics away in firmware sounds like a good idea to me.
Great. Thank you, Andre. Well, with that, we are actually planning to move to a WebEx Q&A now. So this will be more of an interactive WebEx Q&A for folks to have the opportunity to chat with the presenter one-on-one. So I'm displaying the meeting information now if you all don't have it already. So please do feel free to join us there after I wrap up. And then just as a quick note here, thank you everybody so much for joining today, the next webinar in the UEFI 2021 Virtual Plug Fest. Thank you, Andre, for presenting.
Megan, can you paste the link in the
Yep,
chat? Or?
the link is live.
Okay.
And then, yeah, just to mention here, the slides will be available on the UEFI website, and this recording will also be available as well. So thank you all so much.
Thanks.